Okay, so now we're going to look at the third and final rock type, and that's metamorphic rocks. So let's start with a question. What do you think happens if you were to expose, let's say, a sedimentary rock to the heat of igneous forces or to the pressure of tectonic forces? What's going to happen? Well, that sedimentary rock is going to change under the influence of those forces. And it's the change that then produces a new rock type, or that what we call a new rock type, and that class of rocks is called a metamorphic rock. Okay, so this is the third rock type, and it fits into that rock cycle that we saw before, this diagram here. Okay, so a metamorphic rock changes because of heat, pressure, or also fluids from hot water, but that's a separate case which we'll look at the end. Most metamorphic rocks are changed because of huge amounts of heat or large pressure that actually change the makeup of the rocks themselves. Okay, so what are the changes that can occur? Well, the changes can occur in the texture of the rock, which is the size and the shape of the particles. Can also make changes to the minerals in the rock. Heat and pressure can change the minerals. So, as we should know, heat increases with depth into the earth. Now that increase in depth is called the geotherm, and as you go deeper, it increases in temperature, and it ranges between 20 to 50 degrees per kilometre. In fact, if you've ever been down a mine, some good ones around Broken Hill, you don't have to go very far into the mine beneath the Earth's surface to feel an increase in temperature. And that's coming from the core of the Earth. It's coming out. It's coming, that energy, that heat, you can feel just below the Earth's surface. It's quite significant. And miners often have to have trouble dealing, or certainly in the past, dealing with that heat. But the rate of increase will differ depending on the environment that you're in around the Earth. So it'll increase more rapidly in more tectonically active places, such as in around where magma is closer to the Earth's surface, and it'll increase more slowly in more stable or tectonically less active areas, purely because of the proximity of magma chambers near the Earth's surface. Okay, so the simplest way to think about metamorphism due to heat is like pottery being fired in a kiln. If you're making a pottery pot, you take your clay, soft, wet clay, and you can think of that as being a soft, wet clay stone. Sure, it's not as soft and it's not as wet, but it's certainly you can still scratch it with your finger, shales and clay stones, and it'll have some moisture in it. Now, if you put that clay into a kiln, what happens? Well, it becomes harder, doesn't it? You take it out, it's no longer soft and squidgy. The water's been driven off, and somehow that clay pot is now hard. Well, the same thing happens to rocks as a result of exposing it to high amounts of heat. Now, one way that can happen is by coming in contact with magma. So as magma rises through the Earth's crust, as it pushes through layers of sedimentary rock, it's going to come in contact. Now, the changes that occur as a result of the heat of that magma affecting that sedimentary rock, we call contact metamorphism. And it's not a huge area, it doesn't occur over a large area. It occurs over smaller areas, which could be meters or tens of meters, or in rare cases, hundreds of meters, around that magma chamber, just in a thin halo around that magma chamber. So these diagrams here show the location of that contact metamorphism. And so contact metamorphism, we say, is heat only. Okay, so by the vast majority of the affecting process is heat. And so that zone around that magma is going to alter the rocks, and it's going to affect it like it's being baked or put into a kiln. So it's going to form a new rock. Now, what it does to that rock will depend on what that parent rock, or the rock it's moving into, is made up of. If it's a sandstone, what do you think is going to happen? Well, it's going to melt those particles of sand a little bit. And so what happens is that the crystals of the particles of sand will melt a little bit, and they'll melt into slightly larger particles. Any gaps, any pore spaces, which is the spaces between the particles in a rock, will disappear because the edges of those particles of sand will melt and will fill any of the gaps, and that'll tend to glue the particles together. And you end up with a rock that is harder, is less porous, and is a metamorphic rock. And we call that rock quartzite. And this is an example of quartzite. You can see it differs quite significantly to sandstone. It's harder, it's slightly shinier, and that's what happens when you subject it to heat. If the parent material is claystone, the same things are going to happen. Those clay particles are going to melt slightly, and they're going to increase and fill any pore spaces, and they're going to become harder because you melt them slightly, and when they become solid again, it's a much harder rock than the original sedimentary rock, which is just sort of pushed together and glued with a little bit of the cement that was formed that occurred at the time of lithification. Melting particles in a rock makes it much, much harder. And so if you start off with claystone, the particles will melt slightly and you end up with a new rock called hornfels. So again, it's a harder rock than the claystone or the mudstone or the shale that we started off with. So these are two common types of contact metamorphic rocks, quartzite and hornfels. All right, so that's just heat. So let's introduce pressure to the heat we've been looking at. And you can look at heat and pressure on a continuum. Start off with some low heat and pressure and go up to the maximum. Now, where do these occur on the Earth's surface? Well, the lowest amount of heat and pressure occurs at depths that are just being influenced by the pressure of the overlying material. So as it's buried more and more and more, the pressure increases slightly, it becomes hotter, the friction of that burial creates some heat, and you can get this low heat and pressure occurring. Okay, so that's just in large sedimentary basins. If you increase the heat and pressure, where is that likely to occur? Well, areas that are tectonically active and folding will usually have much higher and certainly much higher heat and certainly much higher pressure. So the pressure of the folds is now not just from burial, it's actually from the moving of the tectonic forces. Okay, so these folds then start to affect the area of a much wider area. So it's not just the contact metamorphism, it starts to affect a wider area, and we call that regional metamorphism. So when you get pressure occurring, you get more and more friction, and that's where that starts to increase the heat, and that occurs over a wide area. So that's our sort of middle zone of heat and pressure. And then the third area where we get the highest heat and pressure is going to be in highly tectonically active and volcanic areas where you get both pressure from the moving plates and you also get heat from magma that might be present at the same place. So this occurs in mountain building areas where you get melting of parts of the crust. You get pressure from such as subduction zones or continental convergence that we saw before. That's where you have the highest amount of pressure and the highest amount of heat occurring. So the rocks will be affected most in those areas. Now the term that we give to this change from low pressure to high pressure is grade. Rocks that are affected by the lowest amount of heat and pressure, we say are low grade rocks. Rocks that are affected by the highest amount of heat and pressure, we say are high grade metamorphic rocks. So, looking at the effect of heat and pressure on different rock types. Let's say we start off with mudstone. Now, mudstone contains what? It contains mud. And mud is broken down particles of what? Feldspars and micas. Can you remember that from way back? And are these weathered and eroded particles beach balls or paper? I told you to be important. They're paper, okay? They're like paper. They're small, but they are flat like pieces of paper. So where you have the lowest grade or the lowest amount of pressure, you might get some of those flat particles starting to line up. Different to just the collection, just the burial amount, which gives a shale if it doesn't go any further. But if you get some pressure occurring in that medium grade, that low grade rock, in that regional metamorphism, those particles might line up. And if the particles are then affected by some heat as well, they will grow slightly larger and start to melt into one another. And that's formed our new metamorphic rock. It's no longer shale, but we call it slate. Slate is a much harder rock and it has a very flat surface to it, which is the particles of clay lining up under that pressure. Now, if you increase that pressure a little bit more and you have a bit more heat from the friction from the pressure, then those particles of clay will start to melt even more and start to melt back into one another, and they will be converted back into larger particles of their original minerals. And so what we have in, say, a slate, which is very, very fine particles of the original clay, the particles under a bit more heat and pressure will start to grow a little more, and they'll start to look a bit more, they'll start to develop a bit of shininess to them. You can sort of see here in this rock that there's a little bit of shininess to this rock. Well, that's an indication that the clay particles have started to grow a little larger and form back into particles of mica. And they're large enough now to catch the light, and the light bounces off those crystals into our eyes. So this is a slightly higher grade metamorphic rock. And the name we give to this rock is phyllite. If you then continue to increase that heat and pressure, perhaps it's a bit deeper into the Earth's crust, bit more heat, bit more pressure, then those particles start to grow even more and grow larger and larger and larger, and we suddenly get these extremely shiny rock because the particles are now much larger and they've grown so large that they can reflect the light into our eyes. So we call this one schist. And then if you take the same parent material, that same mudstone, and it's subjected to the highest amount of heat and pressure, then those minerals grow really large, and any mineral that's in that mudstone, which could in fact be other minerals like feldspars, remember, not just mica, could also be feldspars, they start to grow very large and arrange themselves into different bands and can give us a rock like this one, which we call gneiss. Now, the key thing is that all of these rocks, slate, phyllite, schist, and gneiss, were all once upon a time mudstones. It's just the different amounts of heat and pressure that have occurred to change them into different types of metamorphic rocks. It's really important to understand that. So if you're standing on the top of the Victorian High Plains and you see a whole ridge of phyllite, you can go, oh, that's a metamorphic rock. Oh, once upon a time, that must have been a sedimentary rock called shale or mudstone. We must have been somewhere where the water was very still to allow those mudstones to be deposited. And in fact, that's true. It was the bottom of an ocean in the Victorian High Plains that once upon a time then folded into the large mountains. And that process of folding, the tectonic forces that created those mountains, created a new rock type called phyllite. There's slates and phyllites up there and some schists. Okay, see how it works? Now you're probably wondering, maybe you are, maybe you aren't, well, what happens if something like sandstone is pushed by lots of pressure and heat? Do its particles line up? Well, not in the same way, because they're not pieces of paper, they're like beach balls. So they don't they can't line up because the physical shape of their crystals doesn't lend itself to lining up into nice flat layers, or doesn't lend itself to alignment. So a sandstone, if it's under heat and pressure, doesn't really take on a new features in the same way that mudstones do. You can get some sort of squashing of those minerals that you can see sometimes, but it's kind of rare to see, and I've never really seen it in a sample of quartzite. Generally, the particles just tend to get large and form a much harder sort of sugary appearance in that quartzite rock. The last thing to talk about is changed rocks as a result of hot water. We call that hydrothermal metamorphism. Now, you've probably all seen this somewhere. If you ever walked along a beach, an exposed rock somewhere, a riverbed, and looked at a rock and there are these white lines through them. Now, there could be an igneous rock in there, but more commonly, it's likely to be a quartz vein. How does it get in there? Well, clearly it's come after that original rock was put there, and it's been formed within a crack in the rock. Now, how does that occur? Where does the quartz come from? It doesn't come from a magma, because that would make much larger changes. What's happening is that you've got a heat source in the Earth's crust, and you've got water moving through the crust, the Earth's crust. Water from the surface goes down into the groundwater, it goes into the rocks themselves, passes through cracks, through pores over millions of years, and will, by the force of gravity, get closer to that heat source. Where that heat source then interacts with that water, it'll superheat it back into highly, under pressure, superheated water. It won't turn it into steam because there's too much pressure, but it'll heat it to very high temperatures, so high that the temperature of that water will be high enough to dissolve certain minerals from the rocks that are around it. And one of the most common rocks that will melt under the temperature of water that's produced by this hydrothermal source is quartz. And so it'll dissolve the quartz into that water, and the water will become supersaturated with quartz mineral, with silica dioxide. And it'll force it back up, because it's hot, it wants to go back up, and the pressure from underneath of more water coming up forces that water up into the rocks above it, and finds a crack, and then eventually gets far enough away from that source of heat, then starts to cool, and the concentrated silica in that water will then cool and precipitate out into quartz crystals, and it'll solidify into those cracks. That's where you get quartz veins from. Now, the other curious thing is that the other thing that is dissolved by that temperature of that water is gold. So any gold that's in the rocks will be concentrated into that water, and that's why you often have quartz veins and gold in the same place. Now, gold is a much rarer, on the Earth's surface, whereas quartz is everywhere, and so it's quite rare to find gold, which is why it's expensive and why it's good when you find it. So more commonly than not, you'll just have quartz. But if you see a quartz vein, have a look for some gold, because you never know. Okay, so that's the end of the section on rocks.